Modern enterprise systems capture billions of data points every second. Yet, for most organizations, the expected return on this information fails to materialize. Scaling up storage capacity to handle massive volume, velocity, and variety does not yield intelligence. It simply yields a larger archive. Raw data is inherently disorganized, and without a structured mechanism to filter and evaluate it, the information remains unusable. Translating that raw noise into actionable intelligence requires a specific architectural framework. As outlined here in Unit 4, the solution is the construction of a big data processing pipeline. This pipeline is an integrated, multi-stage computing solution. It is engineered specifically to ingest, process, and analyze petabyte-scale data, operating in either continuous real-time streams or scheduled batch modes. The difference between a company that hoards digital noise and one that engineers business intelligence comes down entirely to how efficiently they build and maintain this architecture. To understand how this works, we have to build the pipeline block by block, starting at the boundary between the external world and internal infrastructure: data ingestion. Ingestion is the strictly defined process of collecting varied, unstructured data from external sources and bringing it securely into the pipeline. This text explains ingestion relies heavily on service bindings. These specific connectors allow systems to identify, register, and pull data. Social media or financial data is accessed via web APIs, while sensor data relies on IoT middleware and service gateways. Once data crosses the threshold, it must land immediately in a data storage layer. Traditional databases quickly overwhelm under this throughput. To handle petabyte-scale influxes, organizations implement distributed storage systems like the Hadoop file system or massive cloud buckets. This storage layer optimizes high-efficiency data query and retrieval, ensuring that the heavy computational engines further down the pipeline are never starved for inputs. If ingestion connectors fail to capture data or the storage layer bottlenecks its retrieval, the pipeline chokes before the analytics layer even registers an event. With the raw material secured, we pull it from storage into the data processing layer. Processing is the computational heavy lifting required to clean, filter, and transform messy, disparate datasets into a standardized format. Algorithms perform vital aggregation operations. They remove redundant duplicates, extract the specific features needed, and perform imputation, the statistical estimation and insertion of missing values, to ensure the dataset is mathematically complete. It is vital to note that processing only makes the data usable. It does not generate insights. The polished data is then fed into the data analysis layer, the mathematical engines of the pipeline. This document clearly separates the two functions. Step 3 cleans and transforms raw data to make it usable. Step 4 takes that usable data and applies statistical methods and machine learning. The analysis layer is where hidden correlations are unearthed, and actual predictions and decision-making support are finally generated. Together, these two blocks form the engine room, where raw, historical bytes are officially converted into high-value intellectual property. The final sequential step in the process is data visualization. Complex machine learning outputs must be translated into accessible charts and dashboards for business leaders. But these 5 steps don't execute in isolation. They are driven by an overarching control plane: data orchestration. Orchestration schedules tasks, coordinates data movement, and ensures resources are allocated in the exact correct sequence. Finally, the entire pipeline sits on the foundational layer of data governance and security. As this text dictates, governance ensures the data remains accurate, mathematically consistent, and strictly compliant with privacy regulations at every single transition point in the system. If workflows require manual intervention or data exposes the company to legal vulnerabilities, the most advanced analytical model in the world becomes a liability. We now have a complete 7-part architectural pipeline operating continuously at scale. Massive chaotic inputs are drawn through service bindings, secured and scalable storage, systematically cleaned, mathematically analyzed, and finally rendered as visual insights. Mastering the mechanics of this flow is the primary requirement for understanding modern big data integration. Specific database brands, analytic tools, and programming languages will constantly evolve, but this core functional blueprint, the sequence of operations, remains the standard architecture across the industry. The practice of data engineering is defined by the architecture of this resilient, automated pipeline. the system that brings mathematical algorithms to